was right in this area was greater by the time it built up. That's a reason it happened where it did here. It didn't happen up by Madrid, by Scott City, because you're right at the edge of the Ozarks escarpment there. The embayment wasn't as deep, so you're not getting as much deposited there. A lot of it's washing on down and being deposited in the deeper water like where we are now. The water was pretty deep here 10,000 years ago. And that's a big, like I said, some places around Sykeston, it's close to 1,000 feet to any consolidated material. So that's still building, it's not getting any less. And that's what will cause additional earthquakes is the weight of that.
Well, can't guys like you determine what that weight, what's going to trigger the larger? I mean, you know, you can see, I don't know how you measure the weight now. I don't know by taking your cores and seeing the different composition of the different materials. But can't you say, okay, we're at 10 tons now. When we get to 15 tons, that's when it's gonna, if that's what determines when the actual event happens, is that?
Yeah, that's a difficult problem. For about 6 years, I was a part of the Department of Interior Systems Analysis Group in Washington, D.C., and we did environmental modeling. And what you're talking about is a big engineering problem. You can make estimates of weights based on cores because in this area it spreads out. There are layers beneath us here that extend over probably most of the boot heel area. You may be able to say, well, here's a layer of sand that's 3 feet thick that extends over the whole area. Well, you can make some calculations and determine about what the weight of that would be. You can make calculations about the sediment load that's coming down and how much is deposited. Now the channelization of the river, what the Corps of Engineers has done, probably alleviates this to some extent because it moves everything on downstream. That's why New Orleans is a lot farther from the coast than it was when it was built. It's the distributary of all of the material that's coming out of the Mississippi and fanning out to form the delta. That's why there's a little town up here called Delta. All of this area was essentially a river delta 10,000 years ago, depositing all this material. And so the channelization of the river, now then they tried to offset some of the problem that they made with flooding farther down river by the diversion channel, which is just south of Cape Girardeau. There's a huge channel there that spreads out and all water can come out of the Mississippi and go laterally so that it isn't all going down in a big peak and flooding and topping the levee banks down here. Part of the reason they had to do that is because of the channelization they were doing in the first place and the dredging they were doing, which speeds up the movement of the water down the river. So you have to have some place for it to go. Well, now that also means that a lot of that sediment's going out there. But unless you keep dredging that and dredging the channels, it's going to keep depositing and keep increasing the weight, and that weight will increase on the New Madrid Fault, the Jackson Fault, the Wabash Fault. They're all kind of interconnected, and at some point, but yeah, you can do calculations like that. But like you mentioned, Ivan Browning, he had some very logical reasons that he was predicting the possibility of an earthquake. The problem is people take things, especially the news media, take things very literally. Oh, we're going to have an earthquake on whatever the date was.
16th, I think, December 16th, wasn't it close
Yeah,
to
that sounds right.
Historical date?
You know, all he said, I've read the accounts of it and everything, and all he really said was because of he had a number of factors that he said that could have an effect, and because they all kind of added up on this one date, it would be a probable date for something to happen. Nothing happened on that date, so he's a quack. No, he's not. He had some good ideas, you know. You just have to not take things, well, some of you guys are probably engineers. You know you can do engineering calculations and determine with a certain degree of certainty, but you can never be absolutely certain if you have a complex thing. When we were doing environmental modeling, it was interesting because I was a computer programmer in 1959. The first time I wrote computer programs for the UNIVAC in California, when it was a tape-driven computer that filled rooms. And then I was a systems analysis and a programmer for IBM 360. This was in the late 60s, early 70s. Still, the things we can do now on a laptop, we had to have a room full of computers to do. We were doing simulations of environmental systems and trying to make predictions, but there are so many variables in an environmental system, like a river system or a fault zone and things like that, and so many unknowns that you never know. You've all heard of the butterfly effect, for example. There may be one little variable that you're kind of neglecting, that if that changes much at all, it can really cause problems. Well, we do what we call sensitivity analysis. So when we make a model of a system, like a river system or anything like that, we may have 20 variables that we're measuring. And none of them are really independent variables. They're all interdependent. And so we have to do a sensitivity analysis to try to find out which variables are the important ones. And even then, you can overlook things, or you can, so there used to be a saying for computer modeling, garbage in, garbage out. And in the days when I was doing computer modeling for the USGS in Washington, we had two types of people, it seemed like, in our clients, both federal and companies and so forth. They either thought computer modeling and systems modeling was the answer to all problems, and we just put it into the computer and tell them exactly what's going to happen, or they were at the other end of the scale and said, no, you don't know what you're talking about. You're just playing around with numbers, and I have no confidence in it all. So most of the people that we presented our models to seemed to fall in one group or the other. Either they believed, we were like God, and we could tell them what was going to happen on June 15th next year, or you're just a bunch of quacks and you don't know what you're doing. So, but the truth was somewhere in between. We had models that were very good predictive models for smaller systems than the Mississippi River. We had models that what we thought were pretty good confidence based on statistics, because a lot of what you do in simulation is look at past history, and the better data you have in the past, then you can simulate the future. I was project engineer on a worth of stream flow data research project with Corps of Engineers. We were looking at how much river data do you need before you can design a reservoir, a flood control and water supply reservoir that will really work. And so the amount of data you have, a lot of the data we have, a lot of what we've talked about here is what scientists call anecdotal. It's not really hard data. We know a lot of things happen, but we don't have hard numbers to put into a but I'm sorry I didn't encourage you to ask questions.
Yeah, I'm sure he's tired of my questions, because that's all I do is ask him questions. So, if anybody, please, I told him he'd probably have quite
No,
a few.
I like your questions. If you have any more, come up with them, because they remind me of things that I forgot to say.
Dr. Close, how far down, how far south does
That's unconsolidated
sediment,
material,
the
sediment,
unconsolidated.
all the way to the current Gulf of Mexico.
Okay. how far east and west?
East and west, it varies. In Missouri, the escarpment runs through Poplar Bluff. If you go to Poplar Bluff, north of Poplar Bluff, you're on Ordovician age geology, relatively hard rock. South of there, you're just like you are here. You're in, well, there's the Benton Hills or the Crowley Ridge, it's called farther west, is kind of the divider. If you get south of that, then you're getting into the real embayment area and the deep unconsolidated material.
How far east?
East, I'm not as familiar with, but I think it goes to Middle Tennessee, and then it may pinch back in as you go farther south. If you look at the at geologic maps, it will give you some idea, because if there's hard rock, like when you get down to Georgia, you've got Stone Mountain and things like that. That's obviously outside of where this embayment was, but it's roughly kind of a elongated ellipse that goes all the way down to the current Gulf of Mexico.
So for like the sand boils,
Mhm.
I mean, we can look at Google Earth, we can look at the maps. Will it boil again in the same place, or does it just boil there and then the next time it's gonna be, somewhere else?
Good question. I would say there's a good chance that some of the sand boils that were there in 1800s will be reactivated, because there may still be a neck of sand there, or a lineament or a crack. If that crack's still there, if it hasn't sort of closed up, yeah, they're gonna do it again. In other cases, maybe not. You may have enough sedimentation or shifting that changes it, and there'll be a weaker place. Like water always seeks the easiest course, and you're talking about water pressure. Water doesn't compact the way soils and other things do. So you've got this saturated zone, and when you've got movement and force happening, it'll push the water up through the points of least resistance. So I would expect a lot of them will be reactivated, but some of them might not.
So does this mean that, oh,
Sorry.
What's the actual cause of, I mean, we're in the middle of a tectonic plate here, aren't we? I mean, there's no subduction or anything.
Right.
Is it just a fissure that's because of the changing the weight, or the, what's causing all of
That's a good question. My answer to that is that it's mainly the thawing of the glaciers. It was the warming at the end of the last glacial age, that this just happened to be where the rivers formed and where it started eroding and washing down, and then all of this weight got deposited here. I think that's what started the New Madrid Fault, and probably the Wabash, and a couple of the offshoots of this, was just that heavy weight of all that outwash, because there was so much. We don't know what the surface was, say, in Michigan and Iowa and Wisconsin prior to the glacier. We don't know how many mountains were ground down there, how high they were, and how much was pushed down. You can go up in southern Michigan now, and it's like a foreign landscape if you've never been there. There are what are called there are terminal. Let's see, what are they called? They're called cames, and there are what it boils down to. There you'll find big piles of rock, and you'll go over, and there'll be a big pile of rock here. Well, it's where it was kind of pushed down with the glacier. The glacier melted and just left it there. And you'll find rocks in there that'll be flat on one side where they've been scooting along on top of the hard rock as they were pushed down. And some of those eskers and cames and so forth, have terminology for all of them, are really interesting to dig into, because you'll find rock that obviously came from the Canadian Shield, pink granite and things like that, and pieces of it that, like I said, will be just flattened on one side with striations that show that it's been pushed along. So a tremendous amount of mass was pushed down and eventually washed down the river, and that, I believe is the best explanation for why the faults are there in the first place. Because there's no volcanic action. There was earlier geologically, where I mentioned the Ozarks uplift and the St. Francis Mountains. Those were, at one time, there was some volcanism there. Most of the rock that you see over there today is called igneous intrusive because it came up under the ground and under great pressure from above. That's why there's so much iron and lead and heavy metals over there. The tops of those, where there might have been some volcanism, and there's a little evidence of it on the south side of Tomsock Mountain. There's some pumice stone and stuff like that that would only be formed by volcanism. Most of that's been eroded just by rain and wind and freezing and thawing. It's been eroded down because those are extremely old mountains. Like I said, they're older, far older than the Rockies. Yes, ma'am.
So you're talking about how bad it's going to be here where you have this unconsolidated material, but let's say St. Louis sounded like it's above this unconsolidated material. How bad would a bad quake be there?
The book that Ann passed out gives you some idea. This is based on the best data that could be found at the time when I think Dr. Stewart Knox put this together. That gives you an idea of these different shaded zones are different areas of intensity for shaking. And you can see that it goes up up the river systems, up the Mississippi and the Missouri and up the Ohio. There'll be more shaking near the river because there's more unconsolidated material there. But in St. Louis is built on top of cavernous limestone. And for instance, Anheuser-Busch used to keep their beer in a cavern, in a cave, in a natural cave up there. And there are Weldon Springs, if you know where that is, where they did some processing of uranium during World War II, and they have a big problem with that now in groundwater. And those springs are from cavernous limestone that underlies that area. So what happens in cavernous limestone, if the shaking's hard enough, you can have collapsing of those caves. That's why Rio Foot Lake happened, probably, because it's on the edge of the karst area where all the caverns are over in Kentucky. There probably was a big cavern under there, and the shaking caused it to crack, and the overburden was too heavy, and it fell in. And so in St. Louis, there would be damage, definitely. It wouldn't come necessarily from the shock if the epicenter's down here. You would feel it, and you might rattle, it would rattle windows and maybe break dishes and things like that. But the biggest danger there would be subsidence into cavernous limestone, having your house drop into a sinkhole, essentially.
The perspective that we have, that some of these questions you probably sense, is we're looking at where are we going to set up to provide a base installation for support. How so that we would obviously have to pick a spot that had some confidence by someone, provide confidence that this is a good strip of which to land your aircraft, or set up your medical evacuation places and so forth and so on. So we're looking at how far east, west, or south, or north. How close could we be with confidence it's a safe spot to set up?
You need to talk to the geologists and have them give you geologic maps that shows where the structure, the geologic structure, is heavy enough, and there may be points of hard rock that come out that, that'd be the kind of thing you would look for. Because basically, you're looking at like a great big bowl here that's going to be like a bowl full of jelly and it starts shaking, and there's not going to be any place in the middle of it hardly that you can depend on remaining stable. So you're gonna have to find the closest place you can based on the geology. So geologic maps, and there are very detailed geologic maps available. For here, I don't know, maybe somewhere between Cape Girardeau and Poplar Bluff would be a good jumping off point where you have some good hard rock. There are some outliers of the porphyritic rhyolite that's in the St. Francis Mountains that come down into like Carter County and places like that would be very stable. But any place above the Ozarks Escarpment would be relatively, except for cavernous limestone, would be relatively safe. But yeah, that's I think a very important problem to solve.
And once it happens, once you have the earthquake, are there ways to measure how solid? I mean, I'm going to say like an ultrasound that you can look through the ground and say, hey, this has not been impacted, or this has been impacted but not significantly.
Yeah, there are seismic methods. If you get geologists and engineers to look at cores, for instance, I happen to know that east of Sykeston, there's an area under what's the town east of Sykeston?
East Prairie
No.
or Commerce.
Commerce, Bertrand, Charleston.
Yeah, in that area, there's an area of semi-consolidated, because there was apparently, for some reason, a lot of calcareous material, a lot of lime, and it's starting to solidify. When we did drillings there with the type of machine that we get, the sand cores, we could only go some places about 60 feet before we had refusal. We couldn't get our boring to go down any farther. That wasn't hard rock, but it was a lot more solid than most of the area. So there are going to be some places like that, and seismic information and drilling. There's been a lot of drilling up and down by geologists from the different universities, Tennessee and SEMO and University of Missouri. So there's a lot of data out there. You can get somebody to start looking at it and identifying areas that might be safer. I would think that would be a worthwhile project.
Do the epicenters change over time, or they?
Yeah.
I mean, do they remain constant?
Generally, they don't, because in the subsurface there's lateral shifting. Just like if you go all the way down to the molten core of the Earth, that doesn't rotate at the same velocity that the crust does, because it's liquid, even though it's very dense. That's why we have a magnetosphere. That's why it's like a big magnet. Anytime you have charged particles that are rotating relative to their environment, it causes a magnetic field. It's a basis for electric motors. That's why we have a magnetosphere around the Earth, is because of that differential movement. Well, that carries on up through the layers, up into even the bottom of the areas where earthquakes happen. So there's some lateral shifting. So where the epicenter was in 1812, we don't know where it was 200 years before that. We know that the whole area got shook pretty bad because the Indians